David Potter. Dr. David Potter realizó sus estudios de licenciatura en biología en el MIT. Recibió su título de médico y doctorado de la Universidad Johns Hopkins. Se formó en medicina interna en el Centro Médico de la Universidad de Stanford y hematología y oncología en el Centro Médico Tufts New England. Finalmente, realizó estudios postdoctorales en el Centro para la Investigación del Cáncer del MIT, en el laboratorio del Dr. Philip Sharp. Ha recibido diversas distinciones, tanto por su investigación como su participación en la formación de estudiantes, entre los que destacan el Premio Walter por su investigación en cáncer y distinción en enseñanza por la Universidad de Tufts. Recibamos con una calurosa y grata bienvenida al Dr. David Potter.
I would like to thank the organizers of the meeting for the opportunity to speak here today, and in particular Dr. Luis Ferrer. And I'd like to thank the many students who've come from UCAN to work on this project. So this introductory slide covers some of the structural biology that's the basis for the project that I'll be presenting today. And on the left-hand side, you can see a cytochrome P450 nanodisk from Dr. Steven Sliders' lab at the University of Illinois. And this cytochrome P450 complex can be used for spectroscopy and for binding of small molecules to CYP3A4. And this nanodisk was very important for much of the work that we did in terms of finding binding partners for cytochrome P453A4. In the middle, you can see a co-crystal structure that came from this work. And this was developed by Dr. Irina Severkova and Tom Poulos at UC Irvine, and it shows the metformin molecule docked in the active site of cytochrome P450-384. And then finally, using molecular modeling techniques in the college of pharmacy at the University of Minnesota, we were able to run through many biguanide compounds in the feasible chemical space, and we found a lead biguanide, hexyl benzyl biguanide, which we then used in our further studies. And this slide summarizes the model that we were testing in the work I'll be showing you today. And the idea is a novel one that icosanoids play a role in regulation of the mitochondrial electron transport chain, and that arachidonic acid is epoxygenated by cytochrome P450-384 in breast cancer cells and other cancer cell types, and the epoxygenated form of arachidonic acid can then interact in a way as yet unknown the electron transport chain and accelerate the electron transport chain, thereby promoting the synthesis of ATP, providing some of the energy needs from oxidative metabolism for the breast cancer cells. And so the highlights of what I'm going to talk about today, that CYP3A4 is an arachidonic acid epoxygenase enzyme that is required for breast tumor formation, that CYP3A4 suppresses autophagy in breast cancer in part by inhibiting AMPK activation, and autophagy can be an escape mechanism for breast cancer cell survival. That CYP3A4 epoxygenase promotes the mitochondrial electron transport chain, and that metformin inhibits breast cancer in part by inhibiting CYP3A4 epoxygenase activity. And so the area in which we are working is an area that has much unmet clinical receptor positive, HER2 negative breast cancer hasn't changed much in the past 20 years. And this, about 40,000 women per year in the US are diagnosed with metastatic ER-positive, HER2 negative breast cancer. And this is the most common type of metastatic breast cancer that we see in clinic. And over the past 4 or 5 years, there have been a number of significant advances. Jose Baselga's work on the introduction of everolimus, an mTOR inhibitor, which can enhance the activity of hormone therapy. In addition, from Richard Finn and Dennis Slayman, the cyclin-dependent kinase inhibitors have improved the time to progression, but unfortunately, neither the mTOR inhibitors nor CDKIs have contributed significantly to an improvement in overall survival, which is really what our goal is. Right now, that overall survival is only about 30 months, and we can do better. And although immunotherapy has shown some promise in the I-SPY2 clinical trial from work done by Reunión and the I-SPY2 investigators, immunotherapy does improve the pathologic complete response rate from about 13% to 30% in the ER-positive, HER2 negative signature, but this has not yet led to approval. So this slide summarizes much of the model that I'll be testing today in the following slides. And the idea is that there's cancer cell intrinsic expression of cytochrome P450 enzymes by the synthesis of these eicosanoids, which I'll show you later, can not only impact bioenergetics, but can also have an impact on mTOR function and the nuclear pore complex. And this is all residing within the cancer cell epithelium. In addition, from Deepak Panagrahi's group at Beth Israel Hospital and Deaconess Hospital in Boston, they've shown that the cytochrome P450 and EET system plays an important role in angiogenesis in cancer, and that there's crosstalk between the tumor mass and the surrounding angiogenesis in the tumor microenvironment. But what's interesting is that the CYPs are different, comparing the lymphocytes, endothelial cells, and cancer, thereby creating some potential for therapeutic opportunities if we can selectively target different cytochrome P450 enzymes. And so we need better chemical probes to probe this pathway. And from this work, we developed an interest in metformin. One of the problems with metformin is that although it has a future perhaps in prevention, it does not appear to have much of a future in terms of therapeutics. And only by understanding the molecular mechanisms by which metformin is active in cancer can we make progress. And to do so, we need really good chemical probes. And as Cheryl Arrowsmith at the University of Toronto says, chemical probes need to be highly specific, in contrast to drugs, which need to be safe and effective. And so this is the dichotomy that we're dealing with as we develop new probes to understand how metformin is working. So let's talk about the rationale for what we're doing. So underlying all of this, there's eicosanoid signaling, and there is a conversion of arachidonic acid through the cytochrome P450 epoxygenase pathway, which is the less studied pathway of arachidonic acid metabolism. The 4 regioisomers, or 4 epoxide positions on the arachidonic acid, have differing activities. And you can see on the right-hand side of the slide, there are various inhibitors and various agonists that have been developed, although the molecular mechanisms by which they actually work are not particularly well understood. But the problem with studying the function of cytochrome P450 epoxygenase products is that, on the other hand, there are these epoxide hydrolases which are in the cytoplasm and serve as a shield to break down and immediately destroy these signaling molecules, so that after they've done a very brief signaling job, they're rapidly degraded. And so the standard test for an epoxide hydrolase inhibitor is whether it promotes aortic ring relaxation in a vascular model, and for EETs they do the same, but they're rapidly degraded. And then antagonists are classified by their ability to block this relaxation event. And so at the bottom, you can see, in the bottom right-hand corner, you can see one of the EET regioisomers. So how do we get into metformin? And this slide that I'm showing you is really the pivotal slide that led us in this direction. So Dr. Stephen Woden Laboratory was interested in how these EETs affect signaling in breast cancer, and in particular, estrogen receptor positive, HER2 negative breast cancer. And so these are MCF7 cells, and what he was able to show is that if you knock down CYP3A4, the breast cancer cells grow poorly, and when you look at phospho-STAT3 in the nucleus, phospho-STAT3 is diminished. When you add back the epoxy icosahexaenoic acids, the 14-15 regioisomer type, the nuclear phospho-STAT3 is increased. And so this really was the seminal slide that led us to thinking about how to attack this problem in terms of chemical probe and also drug development. And almost simultaneously with Sijin's finding, Ann Thor's group at the University of Colorado discovered that metformin was inhibiting STAT3 phosphorylation in breast cancer. And so putting 2 and 2 together, this led us to investigate the role of CYP3A4 in breast cancer growth, and also whether one could inhibit the CYP3A4 functional pathway and biosynthesis of EETs using metformin, and then could we develop a better metformin from that work. So we took the CYP3A4 knockdown cell lines and planted in the mouse memory fat pad, and we found that these MCF7 cells did not grow. And what they did was they formed these small nubbins of tumor, which were not palpable, and in which angiogenesis was inhibited. And so this led us to thinking that the CYP3A4 was playing an important role, and that these effects of CYP3A4 were likely to be pleiotropic, that there were effects on angiogenesis, that there were effects on cell proliferation, and there were effects on cell viability. So in the growth curves that you can see in panel A, you can see that the control MCF7 cells with scrambled siRNA grow just fine, and the knockdown tumors do not. So is CYP3A4 present in breast cancer mitochondria? Because we're thinking about metformin and STAT3 signaling, we're thinking about, is there a localization of CYP3A4 in the mitochondria? And in fact, we found that to be true. And so if you look in the bottom panels, you can see that there is a correlation between CYP3A4 overexpression and the mitotracker red. And so red plus green, the CYP3A4 makes yellow in the merge. And one of the things that was interesting is that the mitochondria that were positive for CYP3A4 appeared to palisade around the nuclei. And this was an important clue for later studies on nuclear transport. So, because the EETs are rapidly broken down, we need to use chemical probes that are stable in the presence of epoxide hydrolases, because there's this whole phalanx of epoxide hydrolases at the cell membrane and in the cytoplasm that will break down these molecules before they ever get to the mitochondria and before they can affect bioenergetics. So using the efflux analyzer, what we found is that OCAR, oxygen consumption rates, were increased by a soluble epoxide hydrolase inhibitor that stabilizes EETs. But there was very little, if any, effect on lactate production or the ECAR, the extracellular acidification rate, in the surrounding fluid around the cells. So John Emig and Camille Falk designed a third-generation EET analog, and it contains a urea group that mimics the epoxide, and it contains a charged polar group at the head and a requisite alkene. And this compound does the aortic ring relaxation that I told you about, and it also plays an important role as an EET superagonist, if you will. And so when we have the EET analog C22, we can actually increase oxidative phosphorylation. And when that happens through a pivot mechanism, which we think is mediated through PKM2, we actually see a reduction in lactate production when you get a very robust activation of the electron transport chain. And in contrast, the inhibitor 1450-EEZE suppresses OCAR and ECAR and activates AMPK. So the question then was, does CYP3A4 affect AMPK alpha? And specifically the AMPK alpha 1 isotype found in breast cancer cells. And so we looked at our stable knockdown cell lines, and we found indeed that phospho-AMPK is constitutively present, and that those cells are in a state of constant autophagy. When you add EETs, in contrast, AMPK phosphorylation drops, suggesting that there is a reciprocal relationship here. And this is in contrast to the vasculature, which has predominantly AMPK alpha 2, where the opposite effect is seen. And so by paying attention to the isotype of AMPK that was present in the tumor epithelium compared to the tumor microenvironment vasculature, was very important to help work this out. So then from Anne Thor's group and from Michael Pollack's group work, we started thinking about whether metformin can substitute for the CYP3A4 knockdown. So we know that metformin activates AMPK, and we know that it inhibits the growth of breast cancer cells. But as Michael Pollack was quick to point out, this was at 5 millimolar concentration. And so the cells are basically being pickled in metformin, and our patients don't get dosing that anywhere approaches what we're using in tissue culture, and probably not even in animal studies. And so the question then was, does metformin inhibit CYP3A4? And if it does, what metabolic products of CYP3A4 are regulating AMPK? And so what we found is that metformin inhibits the arachidonic acid epoxygenase activity of CYP3A4, and then can we design a better biguanide? And so this is looking at the synthesis of EETs by metformin, and as expected, the metformin has an IC50 in roughly the 5 millimolar range, and if you add metformin to breast cancer cells, EET levels are diminished. And so, this shows the co-crystal. What we did after getting these results, we sent metformin to Tom Poulos and Irina Sobrikova, And they found that the metformin was situated in the active site of CYP3A4, hydrogen bonded in a very unexpected way with arginine 212. And this was a bent shape of metformin. And what was happening is it was blocking the epoxygenation of arachidonic acid. Now, what's interesting, and CJ published this recently in a paper that came out this fall, other CYP3A4 inhibitors don't do this. So if you take itraconazole or you take ritonavir off the shelf, they don't do this. And so there's something special about the relationship between the biguanide molecules and the iron center and the active site of CYP3A4 that basically makes this inhibition happen. So the biguanide is very special in this regard. And in some ways, the active site of CYP3A4 is like a giant shoebox, and it can accommodate many different xenobiotics as well as natural products. And it's like a tensegrity sculpture, and that three-dimensional structure really depends on what's docked in there. And so by using the docked form that had the metformin in it, this then allowed us to go through a feasible chemical space of patents that were already out there. And we knew that these biguanide combinations were feasible syntheses, and then we could test them by docking in the metformin co-crystal. And this then led us to hexyl benzyl biguanide. Coming full circle, we could use Steve Sliger's nanodiscs, where we can test by serrate band perturbation whether these biguanides were actually interacting with the active site of CYP3A4. And in doing so, we found that hexyl benzyl biguanide was one of the top hits from the computer modeling and silico screening. And then when we went to the nanodiscs for screening, we were able to confirm that there was interaction. And we found that HPV was 200-fold more potent than metformin and inhibits the same targets. And so as a reality test, recently Jared Schulman's group at Yale had shown that metformin is an inhibitor of mitochondrial glycerol phosphate dehydrogenase. And that's one of the major mechanisms by which metformin is active in diabetes. And so the mitochondrial glycerol phosphate dehydrogenase plays a very important role in gluconeogenesis, and by blocking this, metformin can help lower circulating glucose levels. And there are also insulin mechanisms as well. But what we did was we sent HPV to Martin Brandt's lab at the Buck Institute, Nevada, California, and they confirmed that HPV inhibits mitochondrial glycerol phosphate dehydrogenase with an IC50 right in the 20 micromolar range. So the mitochondrial effects that we're getting in breast cancer basically are in the same concentration range that metformin has, for example, in muscle. And so this gave us a pretty good idea that we were on track and that we were studying a coherent biological mechanism. So we took HPV and looked at the EET biosynthesis and found that the IC50 for CYP3A4 EET biosynthesis was about 9 micromolar, and for CYP2C8, another epoxygenase, which is less potent in converting arachidonic acid or less active, the IC50 there was less potent at about 50 micromolar. And in contrast, for metformin, we're looking at 5 millimolar. So if you look at other biguanides, at metformin, buformin, fenformin, or HPV, for metformin, buformin, and fenformin, we're looking at the 5 millimolar range for IC50. If you look at HPV, it's in the 20 micromolar range. And when you add EETs back, you can partially restore the inhibitory effects of HBV, but you can almost fully restore the inhibitory effects of metformin. So this led to the recognition that there's more going on than simply oxidative phosphorylation, and that there were other signaling pathways that were likely affected, and that there were pleiotropic effects of HBV. So when we look at the effects on OXPHOS and ATP synthesis, metformin has very minimal effects even as you get towards 5 millimolar, and this shows by comparison the more potent effects on estrogen receptor positive HER2 negative breast cancer cells in the 20 micromolar range, and both the oxidative phosphorylation and lactate production both inhibited, and here ATP biosynthesis is also affected. And the expected signal targets were affected, including mTOR and phospho-AMPK, but the kinetics of the inhibition is not entirely clear, and it's pretty complex, and we thought we would delve into that in more detail. In an animal model, HBV has modest inhibitory activity of the MCF7 xenograft, and what we come to learn is that the host mitochondria and toxicity, which is weight loss, is really critical. And it depends on whether you do these experiments in C57 black 6 nudes or whether you're doing these experiments in outbreeding mice, because it's actually internal derived mitochondria that are critical for the host toxicity. And this is an ongoing project that we're working on. And so the biomarkers that came out of reverse phase array analysis included a lowering of mTOR levels and a PKC that's involved in isoform involved in diabetes was also affected. So in summary of the first part of the talk, there are CYPs located in different places in the cell. There are CYPs, oxygenases at the plasma membrane and also at the mitochondria. We think that these are functioning independently, that the ETs at the membrane are activating signaling kinases that then activate STAT3 and also activate mTOR. At the level of the mitochondria, CYP3A4 is increasing oxygen consumption rates, increasing ATP levels, suppressing AMPK, and thereby activating mTOR. So this is a linkage between bioenergetics and biomass assembly, which is critical for cancer progression. And we'll delve into that in more detail. On the other hand, when you add HBV, you inhibit STAT3 and mTOR with plasma, in terms of plasma membrane signaling, and then at the mitochondria, where CYP3A4 is also located, you get an inhibition of the electron transport chain, ATP levels drop, AMPK goes up, and mTOR is inhibited. So biomass assembly is now inhibited as bioenergetics are inhibited. So I went to a very informative meeting at Cold Spring Harbor last fall and had the pleasure of meeting Dr. Alex Soukas, who's a diabetologist at Harvard. And this model that I'm showing here is from his Cell paper showing from C. elegans to humans, there's a highly conserved pathway that's inhibited by metformin. And basically this involves a nuclear pore complex modulation that involves the RAGC subunit of mTOR. So in order for the TORC1 complex to be truly activated, RAGC, which has GTP bound to it, has to enter the nucleus. GTP is hydrolyzed to GDP, and then the RAGC comes back out and joins the mTOR1 complex in end lysosomes, and then promotes biomass assembly. And coupled to this is fatty acid oxidation, and this is from the C. elegans studies, which were done by Wu et al. Soukas lab. And basically, ACAD10, or acyl-CoA dehydrogenase, is normally inhibited. In the presence of metformin, the RAGC transit through the nucleus is shut off. Acyl-CoA dehydrogenase is activated through transcriptional mechanisms, and so beta oxidation of fatty acids is shut off, and so you're basically blocking fatty acid oxidation and biomass assembly simultaneously as the cell goes into a defensive mechanism to deal with this problem. And incidentally, the worms live longer. And so with this model, we asked the question, does CYP3A4 regulate the nuclear pore complex? And we wanted to test this hypothesis with our knockdown cells. And in fact, the CYP3A4 knockdown cells have reduced nuclear RAGC. And when we add HBB and we wait over time, we can also reduce nuclear RAGC levels. And this appears to be a more general mechanism, because if we permeabilize cells and we just add 70 kilodalton fitzdextran and look at nuclear pore function, what we find is that HBB can block that function in MCF7 cells and T47D cells. And this now brings us back to our original observations, and they really do make sense. So in collaboration with Daphne Thomas at the University of Michigan and Bae Young at Daegu, Korea, we have done aqua immunofluorescence of CYP3A4 and estrogen receptor alpha in the nucleus, and we found a very strong correlation between nuclear ER alpha and CYP3A4 in the cytoplasm of breast cancer patients. And so this is across a population of unselected patients, suggesting that these mechanisms actually exist in patients. And we then looked in T47D cells, and we asked, if you add HBV, can you block or lower the levels of estrogen receptor alpha in the nucleus? And in fact, we found this to be the case. So this suggested that not only is this icosanoid pathway regulating bioenergetics, but it's also regulating the nuclear localization of the estrogen receptor. And so this just shows a quantitation in the immunofluorescence. So the working model that we now have is that the icosanoids are providing this missing link between the mitochondria and the nuclear pore complex, and also the mTOR complex as well. So the idea then is that the EETs are accelerating the electron transport chain. They can open the nuclear pore complex and facilitate nuclear transit of estrogen receptor alpha and STAT3. The RAGC comes back out and can accelerate the biomass assembly by promoting the TOR-1 complex. And so we're going to continue to work on this model using a variety of chemical probes and approaches and CRISPR knockouts of various components of this pathway, and hope to make more progress and have more to tell you next visit. And the possible implications of regulation of the nuclear pore complex by the CYPs is that this may provide some rationale for combining an mTOR inhibitor and an estrogen receptor inhibitor, whether you're doing everolimus and exemestane or everolimus and fulvestrant, that what we might be actually manipulating here is not only other aspects of estrogen receptor signaling, but also we may be having some effects on this integrated signaling pathway that links membranes, mitochondria, nuclei, and the mTOR complex. And by having a single molecule that can potentially attack all of these pathways simultaneously, this is not the answer to the cancer problem, but it provides a way in which you could reduce the number of molecules that you're working with in the clinic, and then potentially add other approaches on top of it. And so ideally what we would like to do is move the HBV molecule to a phase 1 clinical trial. We'd like to do it as a single agent so that we really know what the toxicities are of HBV, and then we can look at combinations in the future. So in summary, CYP3A4 is an arachidonic acid epoxygenase enzyme required for breast tumor formation and promotes the electron transport chain, and that metformin inhibits breast cancer of the ER-positive, HER2-negative variety, in part by inhibiting the structural target CYP3A4 and its cognate arachidonic acid epoxygenase activity. And so icosanoids may link the ER-alpha signaling pathway and mTOR function in breast cancer. And I want to thank the Masonic Cancer Center, Dr. Dagny, for the very kind support of this project, which has been a bit of a shaggy dog story as we've gone through trying different possible inhibitors, and now I think we have a candidate moving forward. I want to thank the HOT division at the University of Minnesota as well. And from NCAN, I want to thank Erwin Hernandez, Sebastian Mojar, Victor Arieta Cesar Herrera, Fernando Luna, Diego Hinojosa, Mario Torres, Adela Galva, Rafael Castillo, Penny Perez, and the support of Dr. Luis Herrera. And we also thank the Randy Schaefer Foundation in Minnesota, and in particular Dr. Zijin Guo, and the many collaborators that I've mentioned. Thank you very much for